Our next speaker is Danilo Viazzo from Cummings Aerospace.
Hello, everybody. First of all, I wanted to acknowledge the help that I got from Nathan, another team member on the LADEE team. The whole LADEE team, actually. It was a great environment to work in and develop tools and introduce model-based sort of concept and focus on the simulation, which is what I'm going to talk about. Since all the other presentations have sort of dealt with other aspects, hopefully this will give you a slightly different perspective. And particularly one aspect of the simulation that was somewhat unique to this mission, and was sort of the introduction of multi-domain elements and the integration of those multi-domain elements within the overall simulation products. So this is a chart that you've probably seen before. I want you to think in terms of the perspective of the simulation. We started out with effectively almost a blank sheet in terms of simulation product. And that can be a curse and a blessing. We really had the opportunity to establish elements as needed for our needs and not get bogged down with trying to figure out how existing code worked and whatnot. But basically, we had to essentially create a virtual environment for the flight software to be developed. That was our primary goal. So we were flying effectively a virtual LADEE almost from the very beginning of the program. At that point, it was relatively sparse as a model. But the model itself was developed to sort of continue to support flight software development as flight software development elements were being developed. So the talk today, I'm going to just focus on some basic things. First of all, our model-based development, and in this case, I'm going to focus on the model part of that development, not the flight software part. And more specifically, what were the objectives of our simulation product and how those objectives were implemented using the language and how everything was structured in there. And I'm going to focus on three elements of our simulation that I kind of define as multi-domain. The first one was the interface itself. We tried to sort of apply certain uniqueness to that interface. The other one was the electrical subsystem. The flight software was responsible for controlling and managing the electrical system on board, and so we had to sort of create a surrogate to allow for that development. And the third one will be the thermal model. And then I'm going to briefly touch upon lessons learned. And by the way, I have no song, so unfortunately, it'll just be my hand waving here. From this chart, again, this has been presented before. This talks about, it's really the model-based development, but what I'd like to point out is, again, the idea that the simulation itself had to live a parallel path to that development, had to sort of supply and furnish all the necessary components so that this flight software could continue its development. So all the incremental builds that are being that are listed here were essentially supported by equivalent builds of the simulation. Now, because of the nature of our development, both the simulation and the flight software, at least in terms of the controlling components, were really developed in the same environment, and so they were very tightly coupled with each other. Again, this is another one of those charts that we had before, and again, the thought here is that you see the flight software up there. So we have a flight software element, and right next to it we have our modeling element. And so they have to sort of maintain and be in sync with each other. To support all the other uses, and as part of that, as the software was evolving and was being checked and verified, the models were also being checked and verified. So we were looking at making sure that everything was functioning together. So if something wasn't functioning on the flight software, we had to look at the model to make sure that we weren't messing up on our side. So from the point of view of the simulation itself, really we're looking at two basic objectives, with a third one that kind of came along and became actually more important, and Nathan will touch upon in his presentation. But the primary objective was to sort of maintain a single source of all the model. By itself, it doesn't seem to really mean a whole lot, but the thought was we would have, as a second objective, we would have to support multiple target environment. There was a non-real-time, run as fast as you can, used for analysis, for development, for testing. And then there was a real-time aspect, processor in the loop, hardware in the loop, and we wanted to maintain the same sort of code base, the same models with minimum variation. Now, of course, there was some differences between those environments, particularly in the real time. We had access, we were actually running on top, flight software was actually running on top of CFE and would have all the services and all the command handling, telemetry, and all these things. So we had to, for our workstation simulation, which we did not have access to those elements, include models for some of those things, so that we would have really similar kind of behavior across the two environments. The third objective was supporting mission operations. And there were two sub-objectives that came out. One was training, to be able to allow the mission operation team to be trained before the mission, both in nominal operation and off-nominal operation with fault injection and things like that. And then we had an opportunity to actually use the simulation and the simulator products in actual operation. Again, Nathan will touch upon that in his presentation. The other thing is we also were driving to maintain simplicity and commonality. So, for example, in our processor in the loop systems, where we use two processors, we would have effectively, our simulation was targeted as a CFE application on a separate processor. So we would use the same kind of targeting mechanism and the same kind of process to build our simulation product as we did for the flight software. So there were benefits sort of from that internal reuse. So what did we use as a language? We sort of focused our attention with Simulink. That was our common language. And a real-time workshop, we locked it at 2010B as the release. And within the Simulink environment, we also limited ourselves to native blocks and embedded MATLAB. We didn't bring things like S-function or external code into our simulation product, mainly to maintain a level of portability across operating systems and across target environments. We also leverage MATLAB scripts to do initialization, setup, trigger, code generation operations, and also leverage data files in the form of either CSV file that contained like interface definitions, subsystem configuration data, and also external file that contained more like thermal model data and other things of that sort. The simulation structure itself was followed exactly the same type of structuring that we had on the flight software side. That made the whole process, again, very similar, reused from a conceptual point of view, and allow for somebody to look at the whole Simulink model, if you will, that included the flight software to be extremely consistent across the two boundaries. So basically, that was the decomposition. And we had a very basic definition of how things were going to be decomposed and what made a unit and what made a component. And we sort of followed that to the letter on both sides. And essentially, besides sort of the testing and some of the consideration associated with the, the coding, both simulation elements and units from the simulation could have been ported into the flight software side. Literally, it would have been just tagging them, and it could have become part of an application that would have run on board. So talking about these domains that I mentioned before, the first one that I want to bring up was the simulation interface. Generally, as you deal with different environment, there are native sort of ways that you can interact with those environments. Simulink has a very basic way where you load things into the workspace and parameters and values, and you can start the simulation. And sort of there's a basic way that you would interact with a Simulink-based operation, based simulation. What we wanted to do was to have a common sort of interface to all our simulation product, including sort of the Simulink side. And it was clear that the real lowest common denominator would be the actual flight, the ground sort of interface, the ground system interface. And so the idea was, okay, can we actually do that and support that? Initially, when we started doing this development, again, as part of that spiral, we had a simulation that was built that didn't do much, but we had to be able to operate on it. And so even though ITOS and STOL had not been selected yet, we started that development by sort of creating an initial proto-language, if you will, to define our control structure for the simulation products. As ITOS and STOL were selected for the program, then we built basically a simple parser in MATLAB to ingest these script. There were two types of script, one that would represent sort of commands from the ground, and the other one that would represent uploaded command sequences. And again, we parsed those in, and we reduced them into basically time tag tables inside the Simulink environment. These were elements that, again, would be strictly for the workstation sim, but allowed that to operate like our other products and like the real spacecraft. Tunable parameters was another element of the workstation sim that required a little bit of a mapping on the other side. Basically, we had the ability to initialize parameter in the simulation and control the simulation in terms of its operation. And so the native sort of way of handling that was translated into a memory poke type function on the pill and hill side of the product. From an electrical system point of view, really, we wanted to be able to support and build a model that would support the development of our control system on the other side. So our goal number 2 really was the primary goal there, which was you would be sending commands to switches that would essentially operate loads and other things within the spacecraft, and you would be reading back current measurements and other types of measurements from the system. So in order to be able to model that, we had to sort of create a very basic, non-transient response, very much simplified model for the electrical system. Again, keeping in mind that we had the constraint that we wanted to be able to run in real time with this model, along with running really fast in a non-real time setting. So things that had to be modeled were things like battery power or battery state of charge, solar panel for the inflow of charge, switches that allow the control of the system itself, and all the loads. So that's actually the Simulink diagram that was used in the model. And you can see we actually color-coded units in blue, and there is a one-to-one correspondence to these elements. So we could bring in commands coming in from the flight software as if they were commanding the actual hardware on board. The third goal that sort of snuck in toward the end, although we kept it in the back of our minds as we were building the models themselves, was support for injection of failures. So the idea is, off-nominal performance, off-nominal behavior of the system. And so how can we trigger that? And so that was also included as one of our goals for the overall electrical model. So in terms of implementation, we had one challenge. Again, we started the development of the models and of the software to control the electrical system before the actual electrical system had been completely defined. So there was, things were still in a state of flux from the point of view of what controlled what and how, how many of these switches would be active or used and where they were within the topology of the various boards on board. So we had to keep that in mind in our development. So one of the things was, in a simplification, we figured the battery itself, we could really simplify it and take it to the bare minimum of a sort of an integrator, if you will, of charge coming in and charge going out, and with some consideration in terms of what kind of path that charge was taking in terms of efficiencies. The solar panels, we looked at all the panels on that were all individually within the spacecraft. There's 32 surfaces, but only 30 were actually populated with solar panel. 2 were actually instruments. Switches, fuses, loads, all of those were in a state of flux. People were adding more heaters and taking them away, and all that was not nailed down when we started this development. So the approach was, okay, can we actually vectorize this? And what I mean by that is develop a model of a switch that really represents n of those switches, where n can be sort of defined on the fly, if you will. So that was one of the things we did. And then part of that development was to say, look, you system engineering are changing the design, through the electrical. Why don't we define a interface, a table interface, that can define what your current design is, that lists all the switches, that identifies them by certain names and tags, and how they map to commands and how they map to loads and whatnot. And we can key off those and have our model be configured automatically based on how you set up these tables effectively. So the tags on the table were essentially our relational key index to allow the mapping between the various types of objects in there. So the idea was, okay, by having system engineering define those tables for us, they could be delivered into and used in the model, and we could effectively set up a scripting sort of pre-processing stage that would import all these tables, resolve them, and sort of map them back into the model without having any more human interaction, if you will. So the design could continue to evolve, and we didn't really have to worry about it from a model point of view. And then because, again, the components were vectorized, we could also extend the concept all the way to the fault injection and say, hey, now you have an array that corresponds to the number of switches of this type, and these are the ways that you can fail them. So what that resulted in, this is kind of like an eyeful diagram, but this represents really the switch model. And on the left side, those big blocks over there represent fuse states, different kinds of fuses. On one resettable and one non-resettable, and then on the top there's no fuse for those signals. On the left-hand side there, you have 3 switch type, one being on-off, one being on for a hard-coded period of time, and the other one commanded on for a certain amount of time. And in between there, you essentially had a vector of commands that represented all of the switches, all of the signals, and would get routed through this diagram. The table for the routing were auto-generated based on the tables from system engineering, and would essentially route the signals across and then recombine them back on the left-hand side there back into a full vectorized output of the state of the switches that match the input state and match the input order. So that was all done automatically. So once this was set up, we didn't have to worry about it. Thermal model, another model that was introduced. We had to do some thermal control, and that was, again, introduced to be able to support the development of that thermal control. Again, keeping in mind, all this had to be integrated together and be able to run in real time, or be able to run really efficiently on the workstation simulation. So in terms of heat sources, we looked at external heat sources and internal heat sources: sun, moon albedo, moon radiation, and heaters and other loads that were on board, where are basically heat sources. And the thermal propagation really focused on only the conduction and radiation. So that sort of defined our problem. In terms of the implementation, we used a lump mass thermal model. And effectively, we had a table that was generated using thermal sort of analysis tools that our thermal analysis group had access to and was working to analyze the performance of the spacecraft. So they could actually just dump these tables, which define node and transport characteristics for all the nodes within the model. Now, because they had a control at their end, they could effectively dial up or dial down the number of nodes. They could actually provide us with a whole set of these tables that represented various fidelity, various number of nodes that we could use in our model. The other trick there was to actually tag nodes ID to specific, which are now spatially located somewhere in the spacecraft, to specific thermistors and other heaters. Anything else that had sort of a significance from a thermal perspective, either from a heat generation or a measurement. So that could also be sort of linked in through these mapping inside the model automatically. So as the table would be brought in, you didn't have to worry about it. You just selected what size table you wanted to run. We also capped the rate at which the thermal model would update, because as you start adding nodes, if you run it too fast, you're going to overwhelm any sort of machine you're trying to run on. And we ended up supporting 400 plus nodes in real time with, I think it was about 20,000+ connections across those 400 nodes, running at 10 hertz. Now, the heat sources were also tied to the rest of the system. Again, we're talking about now an integrated simulation, and that's one of the benefits of having this type of setup. Very domain-specific tools will require external inputs in form generally of input files that will have predetermined attitudes and things, and for example for thermal, and then compute their propagation. For us, we just tied those states directly into our model, so we essentially could handle things like eclipses and see the effects of everything together, and also have the heat sources tied to the state of switches and the state of loads, and so everything was sort of tied together. So thermal control now had sort of the interaction with the electrical power control, which had interaction also potentially with the attitude control. And the implementation itself was a relatively simple, short script, embedded MATLAB script that was sort of put inside our thermal model. So in terms of what I would say lessons learned from this approach, first of all, being able to build this parser from a commanding perspective, command interface perspective, having this parser on the MATLAB side that allowed us to sort of ingest this stall script, allowed us to have a single source for all our testing. And now we could have a test script that defined a test that we could run on the workstation, run the same exact test on the pill, on the hill, potentially run it on the spacecraft if we wanted to, because it was compliant with that particular language. That in itself proved to be valuable once the mission ops guys were looking for a tool to validate commands. We could just hand deliver them the simulator as is, and they would have that available to them. In addition, because of the flight software, the control software that the flight software was generated from was part of that simulation package, they also had the latest and greatest. There was essentially almost a zero-time update delay for them to receive a up-to-date version of all the products. From the electrical system point of view, by simplifying the electrical system model, we were able to have it integrated and be able to run it in real time, so that things could sort of operate in there. The modularity and the configurability, so the keying off from table, external table, allowed us to really not worry too much about updates to that model. And we could literally just, new configuration would come in, and we would not have to worry about that. Eventually, they got it nailed down once the spacecraft was starting to be assembled, but you know, it saved us time along the way. And again, the introduction of fault injection capability allowed mission ops on the training side to then come up with interesting and creative training scenarios for their exercises. From the thermal model, you know, we built something that was not considered ready for to be used for analysis purpose, but it was sufficient for the testing of the flight software and for training. It provided effectively a realistic thermal sort of picture of the spacecraft as the spacecraft was flying. The ability to configure and select files also allowed us to go from, a workstation sim where we would want to, maybe we're focused on attitude control and not so much on the thermal, to dial down the thermal model and not have to pay a penalty for having introduced that model into the system from a execution performance point of view. So there were some interesting, benefits from each one of those. But more generically on the concept is that when you bring together all these different domains and all these different, less traditional, I have to point out, that the traditional attitude control, vehicle dynamic, ephemeris information, that pretty much is the standard run-of-the-mill simulation that you see for attitude control. But when you bring in all these other elements together, you can have potentially cost reduction in your program, because you can now have sort of a centralized, integrated place where all these different aspects of your system can kind of play together. Keeping them simple, by the way, it's a way to managing that complexity that you would otherwise have to deal with. But the other thing, as you bring in these pieces, you have to be considerate to the fact that not everybody will be interested and be willing to pay the performance price associated with having that domain introduced in a simulation package. So you want to also put as a balancing act something to dial them down as needed. And so here I have an example of just the types of things that we could do as part of our simulation, where you're actually seeing thermal profiles as LADEE is orbiting around the moon, and how certain temperatures on the surface are going up when it's exposed to the sun and they go down, and at the same time the heater response from the thermal control perspective, where things are getting turned on and off along the way. So that's the type of things that you can start seeing and also observing overall. So that concludes my talk. Any questions?
It looks like this.
Thanks. You mentioned that you started developing your model early in the process, before a lot of the physical objects were finished being designed. So did you ever run into a situation where the inability to model something became a constraint to the real design? Basically, if we can't model it, we're not going to build it that way?
Not necessarily. What we did was to, for example, when we started the development of the simulation itself, we didn't even have a state propagator except for attitude. So we couldn't really propagate the state vector, position, velocity of the spacecraft. And so what we did is we essentially had tables that were available that were representative of an orbit around the moon, and we just played those in the background. So we could keep going, essentially providing some sense that the spacecraft was going somewhere. So there were ways to kind of fake it effectively. But we had to be mindful that, we have to revisit those later and not just assume that, we have that covered.
I guess I'm curious to know how important does the program do programs recognize the importance of simulations like this in terms of their relationship to how you qualify your flight software and how you prepare for ops and all those types of things, and do you treat your simulation with sort of the same degree of rigor as you do your flight software development activities when you negotiate who gets the fidelity and where all those CPU cycles are being deployed? Yeah,
programs generally do not recognize the value. This is almost like, if you have somebody on the team, there were some of us that kind of had done this before and kind of knew that if we kind of lined certain things up on the simulator and we picked certain path, that we would get some benefits down the line. But generally, the programs doesn't see that. Like, for example, for mission ops, the thought was, well, we either live without the simulator or we will buy and build something else. There was sort of that concept all the way through. There was no concept of maybe we can just reuse the simulator all the way through and use it for even mission ops. So that became something that by the decisions that we made along the way, maintaining, for example, the interface common, that was now available to them at no additional effort. So programs generally don't recognize that at the onset. Afterwards, oh yeah, great.
Should have gone there.
Yeah, it's a great idea.
Any other questions? Okay, very good. Thank you. Wait. You have to record.
I'm just curious, did you try to convince the electrical systems and thermal engineers to use Simulink directly?
Generally what happens is, like, for example, for thermal, they have their own tools that are very domain specific. They speak their own language, they're comfortable with that. And so to a certain extent, rather than forcing them to use Simulink and say, you have to use this particular tool, I thought the better strategy was to say, just provide me with the data that I can then reuse inside my model. And that way we can keep in sync with each other without having you to be worried about Simulink and me to be worried about the way your tool operates.
Were there tools built in-house?
No, it was a commercially available tool, and they effectively, for my support, effectively, what they had to do was, tweak the model a little bit and then just hit a button and dump a file.
Very good. Okay, thank you.
All right.